Welcome all. We will do second part of the linear algebra course, METU 62. Today, I'll go over basically what we have done in the first semester. I'll go over definitions of vector space, subspaces, linear transformation, matrix representation, and then tensors, tensor representation of linear map, and so on, determinants and exterior products. So I'll just go over the whole semester in 2 hours. And meanwhile, if you have questions, just ask. And then we will start new stuff on Thursday. Okay, so let me just. Okay, so let me change the board. I keep forgetting this. So let's start with the definition of a vector space. What's the vector space? Vector space is a triple a set and two operations. So B is a merged set. So then we have the following properties. First of all, this set together with this operation is an abelian group. So it's a group where the addition operation is commutative. A plus B is equal to B plus A. Okay. If you have any questions about, anything I wrote on the board, just ask me. Okay, I can give more details. But I suppose that you have seen all this stuff several times. That's why I will not. Yeah. This scalar product. I'll tell you what it is. And this scalar product, so it's an operation. So maybe I should take vector space for the field K. Every vector space is a vector space over a field F. This field can be rational numbers, real numbers, complex numbers, or a finite field like Z2, ZP, or any other finite field. Okay? And this operation is an operation defined on this Cartesian product from K cross B into B. So you take the scalar and a vector and you set this to lambda times B. Okay, so it's a binary operation. Binary operation. And this binary operation is compatible with the addition operation in the following itself. So these two operations are not independent. Okay, they are compatible. Moreover, these operations satisfy the following properties. Where are the Katılabiliyoruz. Ben nasıl cevap yazıyorum? İşte mi? Öyle. Ben mesajı bulmuşum. So what are the properties? They are the following. Addition operation or multiplication operation distributed over addition. So if you add two vectors and multiply by a scalar, this is the same thing as multiplying the scalars with the vectors and then adding them up. What else? If you have two scalars and if you multiply these scalars in the field K, so it's the field and it has its own addition and multiplication operation, right? So here this product is the product of the field elements, and then we multiply these this product with the vector B. So this product and this product are different things. This is the product of two field elements. This is the product of a field element with a vector. And we ask the following. This should be the same as the following. You may just first multiply your vector with the first scalar, and then you obtain another vector, and you multiply this vector with the second scalar. What you should get is this product, okay? So the product operation of the field and the scalar multiplication operation of the vector space are compatible in that sense, okay? Do we have any other property? I guess that was it, right? So if you have a triple of a set and two operations satisfying this, then we just call this widget a vector space over a field K. Okay. Onlar da vardır. Belki onlar şey hani buradan geliyor. So 0 times B should be 0. This is the 0 element of the field. This is the 0 element of the vector space. So there are different zeros. But what it tells you, if you multiply the 0 element of the field with any vector, you end up with the 0 vector in the vector space. I guess we can prove this. So this is not an independent actually assumption or property from this. We can prove this. How? Well, you see, 0 of the field is equal to 0 plus 0, right? Here 0 is the 0 of the field. Therefore, 0 times D is just 0 plus 0 times D. So, yeah, before that, this gets that, right? I should write this gadget. Bunu unutmuşuz. Değil mi?
Yine bahane operation
binary operation yok. No, 0 times V, 0 plus 0 times V. And from this property, I can write this as 0 times z plus 0 times z. So what we see is that this gadget is the same as this one, but this is an equation in the abelian group B, and every element has an inverse. So I can just add the inverse of 0 times B to this gadget. Therefore, I can write the following: 0 times B inverse plus 0 times B is equal to 0 times B inverse plus 0 times B plus 0 times B. Now, since this is the inverse of additive inverse of this gadget, this is 0 in the abelian group D. And here, from the associativity, I can write this as follows. So this gadget plus this guy. So I can write it like this. But they are additive inverse of each other. So this is just 0 plus 0 times B. Here, this 0 is the 0 element in the vector space. So 0 element of the abelian group. And it is equal to this one. Since 0 element is a 0 element to something doesn't change anything. It is the identity element of the abelian group. Therefore, this is 0 times B. Therefore, what we get is 0 times B equals 0. Okay. Therefore, this property is not an independent assumption, but it is a consequence of our definition of vector space. Yes. Let's check. So your friend asks the following. So let me here write this 5 prime, meaning that it is not an independent actual assumption, right? It's a consequence of the previous one. Let me just go to 5 prime. And what about this? So 1 times B is equal to B. Here 1 is the identity element of the field K. And this is any vector. Now let's see why this is true. I guess we should take this as an assumption. I think we cannot prove this. Efendim? Şimdi şunu söylüyorsun, 1 çarpı 1 çarpı 1, öyle mi? 1 çarpı 1 çarpı 1. This is, so 1 times 1 in the field K is just 1. And this is 1 times 2. So.
Hocam, buradan olmaz mı? Benim bölümde kendisi var. İkisinin de ilgili bölümde çalışıyor.
Yani nerede, burada mı çarpacağız?
Yok, şimdi.
Invertiyle çarptın. Ha, şöyle diyorsun. Biri invertiyle çarptın. Bunu şöyle yazabilirim. 1 inverse çarpı 1. Burada da benzer.
Aynı şey.
Buradan bir şey çıkacak gibi değil mi? Şimdi burası 1 zaten. 1 çarpı 1. Bu da yine aynı şey. Bence orada assume etmek zorundayız herhalde.
Şey yapsak olmaz mı ya? Evet. 1 çarpı 1 çarpı B var ya. 1 çarpı B eşittir. Üçüncü sınıfta.
Bak şu.
Evet. Onu karşı tarafa alırsak B eksi 1 çarpı B eşittir. Şey yapacak. Tamam.
Hocam,
Sonra.
şimdi aslında biz burada biri ayrı üzerinden çıkartıyoruz. Değil mi? Yani
This is the identity element of the field K.
Evet.
Hı.
Şimdi biri bir artı ayrıntısını herhangi bir elementi ona çarptığı zaman kendisi vermesi gerekiyor.
In the field K.
Evet.
Hı.
Şimdi biri bir artı sıfır şeklinde yazalım.
Tamam.
Sonra elimizdeki özellikler açabiliriz.
Yani B ile çarptık değil mi? Değil mi?
Hı.
Tamam.
İşte burada aynısını vermiş olmuyor mu? Yani B'ye hiçbir şey vermiş olmuyor mu?
Ama şu 1 çarpı 1 artı 0 çarpı B bu 0.
Hı hı.
1 çarpı 1.
Bu boşluk property değil mi zaten?
Ha?
Boşluk property değil mi zaten?
Evet, bunu assume etmemiz lazım. Yani bu şey değil. Bence öbürlerinin. Efendim? Sanmıyorum. Yani şimdi en azından görmüyorum nasıl kanıtlanacağını. O yüzden beni kabul ediyorum. İspat ederseniz söyleyin. All right, so we have several examples, right? For example, if you have n field K, we may take V to the K to the power n being a positive integer. So elements of V are just n tuples, let's say x1, xn. And we have addition operation. So we go to V into V, just additional n tuples. So x1, xn plus y1, yn is defined to be x1 plus y1, xn plus yn. And we have scalar multiplication defined on the Cartesian product K code V into V, and how it is defined. So whenever we take a constant field element and a vector, we just define the scalar product as just this given. So this is the product we define, and this product is the product of field elements. Each xi is an element of the field. So lambda is also an element of the field. So I know how to multiply lambda and xi's. Okay, I just multiply lambda. And so this then, so one may check that this V, which is Kn, together with this pointwise addition and this pointwise scalar multiplication is a vector field, is a vector space over the field. Okay. Okay. We may consider, for example, matrices, let's say M and N. So let's say, okay, let me write it like this. So this is the set of all n by n matrices Aij with Aij is an element of the field K. Okay. This is also a vector space. Let me call it stage 3. What is the addition? We know how to add two matrices, right? If you have a matrix whose entries are Aij's and another matrix whose entries are Bij's, we just send it to the matrix whose entries are Aij plus Bij. So we just add up the entries with the same indices, okay? Namely A11, A1 and A21, A2 and AN1, AMN plus B11, B1N, B21, B2N, and BN1, BMN. How do we define the addition of this? We just add up the corresponding entries. So A11 plus B11, A1N plus B1N, A21 plus B21, A2N plus B2N, AN1, BN1, AMN plus BMN. Okay. If there is anything you don't understand, just ask me, okay? I'm just going over what we have done last time, last semester. And what is the scalar multiplication? Scalar multiplication is defined this way. If you take any lambda and a matrix Aij, you just send this to the matrix whose Ij entry is just lambda times Aij.
K çarpı V.
Evet, evet, o gidiyor. Another vector space, for example, if we have two fields, one of them is a subfield of the other one. So suppose you have a field and this is the subfield of another field, okay? So a subfield. So, in this case, L is a vector space, can be regarded as a vector space or here. Okay. We have seen some examples of this. For example, I can take real numbers as a subfield of complex numbers. Okay. And C becomes an R vector space. I know how to add elements of complex numbers. And what is the scalar multiplication? Well, actually, any real number can be regarded as a complex number. And the multiplication of a real number with a complex number is just multiplication of two complex numbers. So if you have a real number and a complex number, the way you multiply that, well, this is also a complex number, so you just multiply that. Okay? If you want to write it in more detail, maybe in this complex number, you want to write it like this, but and here are just real numbers, and I is the imaginary number. So multiplication is just number times A plus 5 times number times B. Okay? So this way, C can be regarded as a vector space over the field R.
Hocam,
Yes.
Rasyonel reaksiyonların altı işte. Yani onu satıyor.
Yes.
Onu yapabiliyor muyuz? Yani
Here, of course, any complex number can be written like this, right? Therefore, we may consider 1 and 5 is the basis of C over the field R, right? Because any complex number can be written like this. So, right? So if you take a complex number, I can write just 1A times 1 plus B times 5. And we are just real numbers. Your friend asked the following. Well, there are other fields, right? For example, I may consider rational numbers as one field. So this is one field. And this is the subfield of real numbers. And real numbers becomes a vector space over Q, right? What is the multiplication? Well, any rational is just a real number. So rational, I know how to multiply real numbers. So it's just the usual multiplication. So if you have a rational number and a real number, what is the multiplication here? Just multiplication of two real numbers. Okay. What about the basis? So can we find the basis? Well, it is not that easy. It's not like this. Here, C is a vector space over R, and it's this is the basis. So the dimension is 2 as a vector space over R. But here, R is a vector space over Q, but the dimension is infinite. And actually, it is more than infinite. It's uncountable. Okay, it's not a countable basis. It's an uncountable basis. Of course, you cannot just list elements of an uncountable set, but using some I guess axiom choice and so on, that kind of stuff, you can form a base. Okay. Orada bir şey daha var, bir şey unuttum. Burak Hoca'ya soracaksınız onlara. Hamel basis deniyor ona. Any basis of R over 2 is uncountable. Why is that? If it were countable, since Q is also countable, any real number would be a any real number. Suppose there is a countable basis, so basically like x1, x2, and so on. Countable basis. Okay. If it were like this, any real number could be written like this: lambda 1 x1, lambda and x, and for some lambda 1, lambda and q. But you see, how many such elements do we have? Well, for each real rational number, I have one choice here. So the number of such elements is just q times q to the power. But this n could be also 1, 2, 3, 5, and so on. This means that real numbers can be thought as a subset of the following: Q. So those real numbers which can be written with only one non-zero lambda I, those real numbers which have only two non-zero, which can be written as a combination of these two, and so on. And so on. But this is countable, this is countable, this is countable. Therefore, R becomes a subset of a countable union of countable sets. Countable union of countable sets is countable. Therefore, R would be countable. But we know that R is not countable, so that's a contradiction. And why do we have a contradiction? We have a contradiction because we assume that R has the basis of the Q in this form, which can be written as a countable set. Okay? If you assume this, you end up with a contradiction. So this means R is countable. But of course, that's not. Okay. Therefore, R has a basis over Q, but that basis has to be uncountable. Okay. Okay. Well, şimdi sizin sevdiğiniz şeylere geleyim. Tensörler. Okay, so what is a tensor? Let's say we have two vector spaces. Vector spaces or a field. Okay. A tensor okay. The tensor product of V and W is another vector space. So V tensor W. Sometimes to indicate that these are vector space over K and the tensor product is defined over this field K, we write K here. But if it is already understood what the field is, then we may just omit it. But sometimes you may have to be careful because it's important which field you are using. In that case, you indicate it. But if it is already understood what the field is, then you don't have to write it. So what is this gadget? This is a gadget of formal objects. Formal objects of this form. V1 tensor W1, V and tensor W. Here, Vi is an integer, positive integer. So we have only finite integers. Vi's are elements of the first vector space, and Wi's are the elements of the second vector space. So this tensor product are just elements of this type. But we claim that this thing is a vector space itself. So I have to tell you what are the addition operation and scalar multiplication. So they are just formal objects, like matrices, right? Matrices are also formal objects, right? What's a matrix? It's an array of numbers, right? It's a formal object. And we define how we add them, how we multiply them, and so on. So tensors are something like that, okay? They are just formal objects, and we define how to manipulate them, how to add them up, how to multiply them, and so on. Addition, for example, of two tensors, addition. Actually, before this, we have to they are required to be this formal objects, but they have the following properties. What are they? Anything like this, let's say V1 tensor plus V2 tensor W. So here, if I have sum of two vectors and tensor product with a vector in W, then this is considered to be the same as this one. Okay. So we assume this. So these are formal objects satisfying this rule. What else? They also satisfy the following. Lambda times V tensor W. So this is a vector, and surely lambda times P tensor W is the same as V tensor lambda times W. Okay, as long as lambda is integer. So if lambda is scalar, this tensor product is the same as this tensor product. Okay, I can just take this constant from here to here. So these are the two properties that this tensor product satisfy. Okay, so it's a part of the definition of tensor product. And then we claim that this tensor product is also a vector space over the field K. So I have to define what the addition operation and so on. So V tensor W is a vector space bu arada zaman geçti mi? Yok. Daha geçti. The vector space over two with the following operations. So I have to tell you what the operations are. Okay. Okay, first, the addition operation. So what are the elements of these? Elements of these are just finite sums. So I take two finite sums and I will just send it to some of these finite sums. So if this is say, let's say V1, W1, Vn, Wn, comma, let's say V1 prime, W1 prime, plus Vm prime, Wm prime. I just send this two elements to the following. Right, this is the finite sum, this is the finite sum. I just add them up. So V1 cancel W1. V1, no, Vn Wn plus, okay, V1 prime W1 prime, V n prime, no, Vm prime, and then Wm prime. Okay, I just put those two finite sums back to back and obtain another finite. Okay, and then I have to also define scalar multiplication. A scalar times a tensor product is defined to be another tensor product. How? Lambda times, if I take the tensor product, the time, no, is it there? Is it there? This is W. How do we define this? Well, you take this lambda and put it in front of V or W. It doesn't matter because I know that you may put this lambda here or here. They are considered to be the same. So we may just define this as follows. Lambda times V1 cancel W1. Lambda times Vn cancel Wn. Okay. Actually, I don't need this parenthesis because, you know, this times this defined to be just this gadget. So it means that you may regard this lambda times V plus V cancel W or lambda times V cancel W. Doesn't matter. They are just the same thing. Of course, one has to be careful. You know, this is how we define these operations, but there is always the issue of being well defined, because here an element of the tensor product space has different representations. And we define these operations using those representations. But you may choose a different representation, and potentially you may end up with a different result. And that's not something you want, right? If you want to define an operation, no matter who does this operation, he or she should get the same answer. But depending on the representatives you choose, if you get different results, then that's a problem, right? It's not well defined. So one has to be careful. For example, here, these operations are well defined. What we mean by this, they are independent of the choice of representatives. What do we mean by that? We mean the following. So suppose, you know, we have something like this. V1 plus V2 cancel W, okay? And I want to multiply this by some number. Okay. So by the definition, this is what? You just multiply the first vector with lambda, and then you just take cancel with the second vector. But this gadget is also equal to the following, right? This thing is equal to V1 cancel W plus V2 cancel W. They are equal. So if I multiply this with this vector, but written in this form, I should be able to get the same answer. Let's see if the results are the same. These are equal, but whether this will be equal. So what was my definition? You just multiply scalar with the first vector. So this is lambda times V1, W plus lambda times V2, cancel W. Now, are these the same? Well, yes, because we know that since these two vectors are the same, this can be written like this, right? And this gadget is just, of course, lambda times V1 plus V2 cancel W. So this thing is equal to this thing, which is this. Therefore, they are the same thing. So this is a well-defined operation. Okay. Yani bir şeylerin birbirine denk olduğunu kabul ediyorsanız, ki burada ettik, değil mi? Vektör uzayını tanımlarken dedik ki bu tensör product'ı ben böyle de yazarım, böyle de yazarım. Bunlar benim için aynı şey. Onu kabul ederseniz bu bir sorumluluk getiriyor. Nedir o? Madem bunlar aynı, ben bunlar aynıysa sizin tarif ettiğiniz operasyona göre işte bunu elde ediyorum. Ama madem aynı zamanda bunu elde ediyorum. Peki bunlar aynı mı? Değilse o zaman sorun var. Onu kontrol etmeniz lazım. Tamam mı? Yani sadece bunlar birbirine eşittir deyip geçemezsiniz. Başınız derde girer. Hani her seferinde onu hesaba katacaksınız. Okay. Tabii burada to show that these operations are well defined, we have to also show some other things, like this one. For example, lambda. This is the same thing as this table, right? So this element is the same as this element. So I may multiply this gadget with the scalar, and that should be the same as that scalar times this gadget. So if I multiply this with mu, I should get the same element times mu. Let's see if it is the case. Now, what is this definition? What is this multiplication? Well, my definition is that take the scalar and multiply it with the first element. So let's do that. So this is lambda mu times lambda b tensor w. Okay. And this is just lambda times mu times lambda times b tensor w, right? Because I can just take this element outside. Yok, şöyle desem daha iyi olacak. Bunu gereksiz yere uzatıyorum. Şöyle diyeyim. This is mu times. What is this? This is just lambda times b tensor w. Yes.
Hocam biz zaten bu söylediğimiz
Bir dakika, dur. Şimdi bu lambda ile çarpınca şöyle diyor, evet. Bu lambdayı dışarı çıkıyor. Bu mu çarpı lambda bir tensör kabulü, değil mi? Ama bunu şöyle de yazabilirim. Bunu mu ile çarptığım zaman şunu biliyorum zaten. Bu lambdayı buraya alabilirim. Evet, yani bu bariz zaten.
hocam.
Evet. Evet.
Sonraki produsı için zaten direkt bunu söylemek. Anlamına geliyor.
Yani hemen hemen evet. Evet, gerek yok işte. Yani bu bariz bir şey. Evet. İyi, ara verelim. Aradan sonra devam ederiz. Okay. Pardon, şunu bir durayım. Şöyle.